Okay, today we're going to talk about properties of waves. So resonance, a condition that exists when the frequency of a force applied to a system matches the natural frequency of vibration of the system. We're going to talk about this more in detail next week. We're also going to look at applications. We're going to explore what happened with the Tacoma's Narrows Bridge, which was a bridge connecting Seattle and Tacoma in Washington State that ended up collapsing because at the time the engineers did not realize what resonance did to a bridge. So the wind actually matched the frequency of the bridge and the bridge collapsed. And since then, they started using wind tunnel tests on different things that they designed. So we're going to talk about that whole class next week. So what is a wave? A wave is a disturbance that travels through matter or space. So as the wave travels, energy can be carried from one place to another. So in this chapter, we're going to be talking about mechanical waves. So mechanical waves need a medium to travel through. So what's a medium? Well, a medium is anything that has matter. So a medium can be air. A medium can be water. A medium can be wood. A medium can be a desk. A medium can be anything that has matter. Where is there not a medium? A medium is going to be in space when there's not any matter. So first we're going to look at transverse waves. Now these might be familiar from middle school. So a transverse wave is one that the object moves at right angle to the moving particles. And on Friday, tomorrow, we're going to do a lab using slinkies, and we're going to mimic transverse waves. So we'll demonstrate that tomorrow. So this is a diagram of a transverse wave. Now in physics, we always have to have our frame of reference, where to measure something from. So our frame of reference with a transverse wave is something called the rest position. And there's different parts of the wave. The top of the wave is called the crest. So that's a crest, this is a crest, and this is a crest. The bottom of the wave is called the trough. So trough, trough, trough. Now we can measure different physical properties of the wave. So we can measure how high it is from the rest position. That's called the amplitude. When we want to measure the wavelength of the wave, we measure the wavelength from crest to crest or from trough to trough. Longitudinal waves are the kind of wave that move along the same direction as the medium. We're also going to look at longitudinal waves tomorrow in our lab. So this is a diagram of a longitudinal wave, and a longitudinal wave is a series of compressions and rarefactions. So a compression is where the medium is closer together, the particles within the wave, and a rarefaction is where it's spread apart. Now I can also measure the same properties. I can have a wavelength. So a wavelength is going to be from compression to compression or rarefaction to rarefaction. So the same part of the wave to the next successive part. I can also measure the amplitude of the wave, and I forgot that diagram, and the amplitude would be from here to the top. So that would be the amplitude of a longitudinal wave. So again, a compression, a region where the particles of the medium are close together. And then the rarefaction is the region of where the particles are spread apart. And we can use an oscilloscope to see this when we study sound waves. Now in the next chapter, we're going to study sound waves the week after next. And maybe we'll look at that also with the oscilloscope. Now this is a little chart. Now the reason I put the chart in the notes is for me, personally, when I see things in tabular form or in a chart, it really helps me to conceptualize and see it, especially where I'm comparing and contrasting things. So I have my different parts of the wave. So I have my transverse and different types of waves, transverse and longitudinal. I have the direction in which the wave is moving from left to right, but then I have the direction of the motion of the medium. So for the transverse, as the wave moves from left to right, the motion of the medium is perpendicular. And this shows you how it would look in a slinky, because that's what we're going to do tomorrow in the lab. For a longitudinal wave, as it moves from left to right, it's going to be moving the same direction. And here also is the diagram that we're going to see tomorrow in our lab. And again, the different parts of the longitudinal wave, the transverse wave, we have the crest, which is the high point, and the trough, which is the low point. And again, the wavelength, the distance from crest to crest or trough to trough, the symbol for wavelength is a Greek letter, and it's called lambda. The unit for wavelength is meter. Because remember, this is a type of what? Length. and when we measure length, we measure it in meters. So this is the one equation for tonight's homework, is speed is frequency times wavelength. And some of you might have actually used this equation in middle school. So V, the speed, is equal to the frequency times the wavelength. So V is equal to F lambda. So here's an example. Suppose you generate rope waves with a frequency of 2 hertz. Now remember, a hertz is 1 over a second. You find the wavelength of a rope wave to be 3 centimeters. So this is the wavelength lambda. What is the speed V? So we write our given, and we write what we want to find. We write our basic equation, and we substitute and solve. And in this case, I left it in centimeters because it really didn't matter. Now, there's other properties of waves that we can look at. So the energy of a wave is related to the amplitude. The greater the amplitude, the greater the energy. So we'll see this in next chapter with sound. We won't see it, we'll hear it. Where we put more energy in, the sound is louder. So when a wave passes into a new medium, its speed changes. We also see that when waves meet, and we'll explore this tomorrow in our Slinky lab, that the waves can either add together or cancel each other out. So the principle of superposition says at the point where 2 or more waves meet, the displacement of the medium or the sum of the displacements of the individual waves. So we have something called interference. Interference is where we combine 2 disturbances arriving at the same point at the same time. So constructive interference, is where they combine. So if I have 2 waves that meet, so let's say this one's going this way and this one's coming this way. At this one point where they actually meet, see how they add together and they produce one wave that's twice the size? But then after they pass each other, they continue off going in those directions. Okay? So that's what's called constructive interference. So they're coming together at that point, they add together, and then they go off in their particular directions. Then we have what's called destructive interference. So destructive interference is where they kind of cancel each other out. So destructive interference is, and from my frame of reference, this wave is on the top going this way, this wave is on the bottom. So the one point where they meet, and this kind of doesn't really show it, what happens is you're going to see nothing. And we can actually look at these all tomorrow when we generate waves tomorrow using the Slinkies. So a node is a point in a medium or field that remains unchanged when acted upon by more than one disturber simultaneously. An antinode is a point where the displacement caused by interfering waves is the largest. Now we're going to see in the video next week when we actually look at the collapse of the Tacoma Narrows Bridge, we're going to see that going down the center of the bridge is this nodal line. So we're going to see as the bridge begins to oscillate, the scientist is actually on the bridge, and instead of running down the side of the bridge, he knows that that nodal line is right down the center of the bridge as the bridge is oscillating. And you're going to see in the video him running down the center of the bridge just before the bridge collapses. And he's running down because he knows that's the nodal line, and that's the place where there's the least disturbance during the bridge, on the bridge, right before it collapses. So we'll see that next week. And that's it for today.